Hello everyone, myself Sana HP, studying Computer Science and Engineering in SVCE. My library ID is 23CS1812, subject is Applied Physics. Today I am going to explain about the topic Physical Significance of Wave Function and Born Interpretation. The physical significance of the wave function in quantum mechanics is closely tied to the Born interpretation, named after physicist Max Born. Here, I will elaborate on both the wave function and the Born interpretation. First one is wave function. The wave function is a mathematical function that describes the quantum state of a system. It contains information about the probability amplitude associated with different possible states of a particle or a system. The square of the absolute value of the wave function is phi square gives the probability density of finding a particle in a particular region of a space. The wave function evolves over time according to the Schrödinger wave equation describing how the quantum states change dynamically. Next is Born interpretation. The Born interpretation provides a way to interpret the wave function probabilistically. Max Born proposed that the square of the magnitude of the wave function at a given phi square represents the probability density of finding a particle at that location. Born's rule states that when a measurement is made, the probability of finding a particle in a certain region is given by the integral of phi square over that region. The Born interpretation resolves the probabilistic nature of quantum mechanics and emphasizes that unlike classical physics, pretend about individual events are inherently probabilistic in the quantum realm. Next is physical significance. In their probability distribution, the square of the wave function's magnitude provides a probability distribution for the possible outcomes of measurements. This is a departure from classical mechanics where particles have definite trajectories and properties. Next is superposition. The wave function allows for the superposition of multiple states. A particle can exist in a combination of states simultaneously, and the probabilities associated with each state are encoded in the wave function. Moving on to the next slide. Operators and observables. Operators in quantum mechanics acts on the wave function to represent a physical observable such as position, momentum and energy. The eigenfunctions of these operators are the possible wave functions of the system for those observables, and the corresponding eigenvalue represents the possible measurement outcomes. Next is time evolution. The time-dependent Schrödinger equation describes how the wave functions evolves over time. The time evolution of the wave function governs the dynamic of quantum system. And the next is quantum measurement. The wave function collapses upon measurement. The outcome of a measurement is one of the possible states and the probability of obtaining a specific result is given by the Born rule. Next is uncertainty principle. The wave function is intimately connected to Heisenberg uncertainty principle, which says that certain pairs of property like position and momentum cannot be precisely known simultaneously. The spread of the wave function in position and momentum space encapsulates this uncertainty. And the conclusion is, in summary, the wave function and the Born interpretation together form the foundation of the probabilistic nature of the quantum mechanics. The wave function encodes information about possible states and the Born interpretation provides a rule for interpreting the probabilities associated with those states. This framework has been incredibly successful in describing the behavior of particles at the quantum level, even though it challenges classical intuition about determination and predictability. And thank you everyone for watching the video.